Welcome. Today, we're diving into computer fundamentals, focusing on Unit 3. I'm Sindhu Devi from the Computer Science and Business Systems Department at Jerusalem College of Engineering. Together, we'll explore key concepts that form the backbone of computing, essential knowledge for anyone looking to understand how computers really work. Let's get started. Let's start by understanding what a digital computer really is. At its core, it's a fast electronic machine that takes in digitized information. That's data converted into numbers from the user. It then processes this data by following a set of instructions stored inside its memory. Finally, it gives the processed information back to the user. To make this happen, a computer is made up of 5 key parts: input, memory, arithmetic and logic, output, and control units. Each one plays a unique role in the system. Here, we see a clear breakdown of the 5 key functional units inside a computer. Each unit plays a specific role, and this figure shows exactly where you'll find them physically located within the machine. Understanding these parts and how they fit together is essential for grasping how a computer actually works. Let's take a closer look at each unit and what it does. Let's talk about the input unit. It's where everything starts. This unit takes in digital information from us, using devices like keyboards, mice, or microphones. Once the input unit receives this data, it has 2 choices. It can either store the information in memory for later, or send it straight to the arithmetic and logic unit. That's where the real processing happens, performing the operations we need right away. The program stored in memory guides every step of processing. Once the data is processed, the output is either sent to the user through output devices or saved back into memory for later use. All these activities don't happen by chance. They're carefully coordinated and controlled by the control unit. Together, the control unit and the arithmetic and logic unit form what we call the central processing unit, or CPU. This is the heart of any computer system, managing both instructions and calculations seamlessly. Let's talk about how a computer takes in information. It all starts with the input unit, which uses devices to feed data into the system. The most familiar ones are the keyboard and mouse. We use the keyboard to type text and numbers, while the mouse helps us move the cursor and select options on the screen. But there's more. Joysticks, trackballs, digitizers, and scanners also play a role in getting information into the computer. Each device has its own way of connecting us to the digital world. Let's talk about input devices, the tools we use to interact with technology. These are the keyboards, mice, touchscreens, and sensors that translate our actions into digital commands. Without them, computers would just be silent boxes. Input devices shape how we communicate with machines, making our intentions clear and our experiences seamless. They're the bridge between human intention and digital response. Understanding them helps us design better, more intuitive systems. Let's talk about the memory unit, the part of a computer that stores programs and data. It's usually made up of 2 types of devices: primary and secondary storage. Primary memory, or main memory, is fast and holds programs and data that the computer is actively using. This main memory is built from semiconductor cells, each storing a single bit. The CPU reads or writes these bits in fixed-size groups called words, allowing efficient access to data 1 word at a time. When we want to access data from main memory, each word has its own unique address. This means we can get to any word just by specifying that address. The size of each word, called the word length, usually ranges from 8 to 64 bits. How many words the memory holds determines its overall capacity. So, main memory size can vary widely, from a few million words to tens of millions, depending on the system. Let's talk about memory access time. That's how long it takes to get to 1 word in memory. For main memory, this time needs to be as short as possible, usually between 10 and 100 nanoseconds. It varies depending on the memory type. Random access memory, or RAM, takes a fixed amount of time to reach any word, making it fast and predictable. Sequential access memory, on the other hand, doesn't have a fixed access time. Since main memory uses RAM, it's quick but limited in size and costly. That's why computers rely on secondary storage like magnetic disks and tapes for larger data needs. Today's computers rely on 2 fundamental ideas. First, instructions themselves are represented as numbers. Second, programs aren't fixed. They can be stored in memory just like any other data, read or written as needed. This leads us to the stored program concept. It means memory can hold everything: the source code, the compiled machine code, even the editor or compiler used to create that code. This flexibility is what makes modern computing possible. The arithmetic and logic unit, or ALU, is the part of the processor that actually does the math and logic. It handles operations like addition, subtraction, multiplication, and division. It also performs logical tasks, things like ANDing, ORing, and inverting bits. To work, it pulls data from main memory into fast storage called registers. Each register holds one word of data, often the numbers we need most. Once the ALU finishes its work, the result gets stored back in a register or sent to memory. Now let's look at the output unit, the part that sends the final processed results to the user. This can happen through various devices like video monitors, printers, or plotters. Video monitors show the output on the screen, while printers and plotters provide a physical, hard copy version. Printers themselves fall into two main categories, based on how they print: impact printers and non-impact printers. Each has its own way of producing the printed output. The control unit is like the brain's conductor, coordinating all the activities among the different parts of the computer. It fetches instructions from memory, figures out what needs to be done, and sends out control signals to make it happen. These signals act like precise timing cues, telling each component exactly when to act. It manages input and output, and the flow of data between the processor, memory, and devices. Because it's much faster than most connected devices, it can efficiently oversee multiple operations at once. Let's take a look at the general structure of a von Neumann machine, also known as the IAS computer. It's built around 5 key units, each with a clear role. The input unit brings data and instructions from outside into the machine, guided by the control unit. The memory unit holds both data and instructions together. The arithmetic logic unit, or ALU, handles all the calculations and logic. The control unit fetches and decodes instructions, making sure they get executed. Finally, the output unit sends the results back out. In the original IAS machine, memory had 4,096 locations, each storing 40-bit words, used for both data and instructions. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about the von Neumann architecture, a foundational concept in computing. Here, both the program instructions and the data live together in a single read-write memory. This memory is organized by address, not by data type, so the system treats everything the same way. Instructions run one after another, step by step, unless something changes the flow. But there's a catch. The processor's speed depends heavily on how fast it can access memory. This limitation is known as the von Neumann bottleneck, or the memory wall. Now, let's dive into the detailed structure of the IAS, or von Neumann machine. This architecture is the foundation of modern computers. It's built around a central processing unit, memory, input, and output. What makes it unique is how it stores both data and instructions in the same memory space. This design allows the machine to fetch, decode, and execute instructions sequentially, a simple yet powerful concept that shaped computing as we know it. Let's take a closer look at the detailed structure of the IAS computer. It's made up of several processing and control units, plus a set of high-speed registers like AC, MQ, Doctor, and others. These registers hold instructions, memory addresses, and data. The instruction cycle has 3 key steps: fetching the instruction, decoding its opcode, and then executing it. The program control unit manages this flow, ensuring everything moves smoothly through the CPU. Once decoded, the arithmetic logic unit carries out the actual operations the instruction calls for. Let's talk about timing and registers in this system. An electronic clock circuit keeps everything in sync. It generates the basic timing signals that coordinate all the parts. Now, the program counter, or PC, is an address register. It holds the address of the next instruction to run, so it's sometimes called the instruction address register. Then there's the address register, or AR. It's a 12-bit register that points to a specific memory location, telling the system where to read or write data in the data register. Let's look at some key registers inside the CPU. The data register, or doctor, is a 40-bit register that holds any 40-bit word. It's where data moves between the CPU and memory during processing. Then we have the accumulator and multiplier quotient registers, both 40 bits as well, used to temporarily store operands and results while instructions run. Finally, the instruction register and instruction buffer register work together to fetch two instructions at once. The first goes into the IR to be executed immediately, while the second waits in the IBR. The instructions used by the IAS computer fall into 5 main categories. First, data transfer, moving information around. Then, unconditional branch, jumping to a new instruction without conditions. Next, conditional branch, where the jump depends on a specific test. Arithmetic instructions handle calculations and number operations. Finally, address modify instructions adjust memory addresses, helping the computer navigate its data efficiently. These groups form the foundation of what the IAS computer can do. Now, let's dive into the instruction set of an ISA computer. This is the fundamental language the processor understands, the commands it follows to perform tasks. Each instruction tells the machine exactly what operation to carry out, whether it's moving data, performing arithmetic, or controlling program flow. Understanding this set is key to grasping how software communicates with hardware and how complex programs break down into simple, executable steps. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. In MIPS assembly, each arithmetic instruction does just one thing, and it always works with exactly 3 variables. For example, add a B, C adds B and C, then stores the result in a now. If we want to add 4 variables together, say B, C, D, and E, and put that total in a, we can't do it in one step. Instead, we chain 3 instructions. First, add B and C into a, then add D to that sum. Finally, add E. It takes 3 instructions to get the job done. Let's take a look at the kinds of operations the MIPS instruction set supports. They fall into 5 main categories. First, arithmetic operations, the basic math that powers calculations. Then, data transfer, which moves information between memory and registers. Logical operations handle bitwise manipulation. Conditional branches let the program make decisions based on conditions. And finally, unconditional jumps, instructions that change the flow without any conditions. These categories cover the core actions MIPS can perform. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. In MIPS, arithmetic instructions don't just work with any data. They have to use operands stored in special places called registers. These registers are built right into the hardware, and they're visible to us as programmers. Each register holds 32 bits, which MIPS calls a word. Now, MIPS only has 32 of these registers. That might seem small compared to variables in a program, but there's a good reason. More registers mean slower signals and more complex instructions. So the limit keeps things fast and efficient. Our processor can only hold a small amount of data in its registers at any one time. But computer memory, it's massive, containing billions of data elements. So, larger data sets, like arrays and structures, live there instead. Think of memory as one big, single-dimensional array, where each address is an index starting at 0. Since arithmetic only happens in registers, we need special instructions to move data back and forth between memory and registers. These are called data transfer instructions. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about the load instruction, the command that copies data from memory into a register. It's made up of 3 parts. First, the operation's name. Next, the register that will receive the data. Finally, a constant and another register, which together point to the memory address. The constant and the second register's value add up to find exactly where the data lives. In MIPS, this instruction is called LW, short for load word. It's a fundamental step in moving data around. Let's walk through an example to see how this works in practice. Imagine we have an array, A, with 50 words and 2 variables, P and Q, tied to registers S1 and S2. The array's starting address sits in S3. Our goal is to compile the statement P equals Q plus A of 7. Since A of 7 is in memory, we first load it into a temporary register, T0. Then, we add Q from S2 to that value and store the result back in S1. Linked to P, the number 7 here is called the offset, and S3 is the base register. In MIPS, registers hold 32 bits, so the word size is 32 bits or 4 bytes. Most memories today are byte-oriented, meaning they address individual bytes. But when dealing with words, the starting byte has to line up just right. In MIPS, that means words must start at addresses that are multiples of 4. This rule is called an alignment restriction, and it's common across many architectures. It helps keep memory access efficient and predictable. When working with a 32-bit word size, the way we calculate memory addresses changes a bit. Since each word is 4 bytes, the offset we add to the base register needs to be multiplied by 4. So, to access the element A5, we multiply 5 by 4, giving us 20 as the offset. Now, the store instruction does the opposite of load. It copies data from a register back into memory. Its format is similar: operation name, register to store, offset, and base register. In MIPS, this instruction is called SW, or store word. Let's look at how to translate a simple C assignment into MIPS assembly. We start by loading the value at A7 into a temporary register. Then, we add the value of P to that temporary register. Finally, the sum gets stored back into A10. Notice how the offsets are calculated by multiplying the index by 4, since each array element is 4 bytes. This step-by-step approach helps us handle array access and arithmetic in assembly language. In MIPS, data transfer instructions only read or write one operand. They don't perform any operation on it. Arithmetic instructions, on the other hand, read 2 registers, perform a calculation, and write the result back. Because registers are faster to access and handle more data per second, they're more efficient than memory. But since programs often have more variables than registers available, the compiler keeps the most used variables in registers and moves the rest to memory. This process of moving less used variables to memory is called spilling. Let's talk about arithmetic instructions where one of the operands is a constant, what we call an immediate operand. For example, the instruction ADDI S2. S2, 5 adds the number 5 directly to the value in register S2. This is called an add immediate instruction. By including constants right inside the instruction, the operation runs faster and uses less energy than if we had to load that constant from memory first. Immediate operands make arithmetic more efficient. Let's look at how to translate this C statement into MIPS assembly. We want to assign A10 the value of A5 plus B. Since both A5 and B are stored in memory, we need a few steps. First, we load A5 into a temporary register. Then we add B to that value. Finally, we store the result back into A10. Each memory access uses the base address in S3, with offsets calculated by multiplying the index by 4, since each array element is a word. Let's break down how to translate this C statement into MIPS assembly. We start by loading the values B4 and B3 into temporary registers. Then, we subtract B3 from B4. Next, we multiply the result by 4 since each integer is 4 bytes to get the correct byte offset. We add this offset to the base address of array A to find the exact element we need. Finally, we load that element and add it to G, storing the result in F. Let's break down how to translate these C statements into MIPS assembly code. We start by loading the value of A4 from memory into a temporary register. Then, we subtract that value from F next. We subtract G from F as well. After that, we add 100 to F finally. We store the updated value of F back into A5. To complete these operations, we need 4 registers in total. This example shows how careful register use maps high-level code to low-level instructions. Let's look at how we translate some C code into MIPS assembly. We're working with variables assigned to specific registers and arrays whose base addresses are stored in registers too. For the first example, we need to calculate F equals negative G minus the value at index 5. We load A5 into a temporary register, add it to G, then subtract that sum from 0 to get the negative result. This shows how we handle array access and arithmetic together in MIPS. Here, we're looking at a snippet of assembly code that performs some key operations. First, it subtracts one value from another. Specifically, it calculates I minus j and stores the result. Then, it adds this result to another value, updating the array accordingly. Next, it loads a word from memory into a register, essentially fetching an address. Finally, it stores this address into a specific location, updating the contents of what we can think of as an array element. This sequence is all about manipulating data efficiently at a low level. Let's take a closer look at how registers are mapped in MIPS assembly language. Registers labeled from S0 to S7 correspond to registers numbered 16 through 23. Meanwhile, registers named T0 to T7 align with registers 8 through 15. This mapping helps us understand how the processor organizes and accesses data during instructions. The figure on screen shows this relationship clearly, making it easier to follow along as we work with these registers in code. Let's take a closer look at the R format instruction in MIPS assembly. Here, the instruction is broken down into segments called fields. Each field holds a specific part of the instruction, like the operation code, source registers, destination register, and shift amount. This format is used for register-type instructions, where all the data comes from registers. Understanding this structure is key to translating a MIPS assembly instruction into its machine code equivalent. In the MIPS instruction set, the opcode is just 6 bits long. That limits us to 64 possible instructions. But for R-type instructions, there's a clever twist, an extra 6 bits called the function field. Together, the opcode and function bits define exactly what the instruction does. Then, we have registers to work with. The ARD field points to the destination register, where the result gets stored. The RS field is the first source register, holding one of the operation's input values. Now, let's break down the parts of this instruction. We have the second source register, which holds one of the values we'll work with. Then, there's the shift amount. That tells us how many bits to move in shift operations. Finally, the function field adds 6 bits to specify exactly what operation we want, beyond the main opcode. With these pieces in place, we're ready to translate the instruction add to S1, S2 into its machine code form. Let's break down how this MIPS instruction tells the computer to add 2 numbers. The first and last fields, 0 and 32 here, signal that this is an addition operation. The second field points to the first source register, S1, and the third points to the second source, S2. The fourth field is where the result goes, into register T0. The fifth field isn't used, so it's just 0. Put it all together, and this instruction adds S1 and S2, then stores the sum in T0. Now, let's look at a second type of instruction format called I-type, or immediate format. This format is used mainly for immediate and data transfer instructions. It's structured with specific fields that define the operation, the registers involved, and the immediate value itself. Understanding these fields helps us see how data moves quickly and efficiently within the system, making I format essential for many common operations. When we talk about a 16-bit address in this context, it means a load word instruction can access any word within a range of plus or minus 32,768 bytes. That's 2 to the 15th power. In terms of words, that's plus or minus 8,192 words, since each word is 4 bytes. This range is centered around the address stored in the base register, called RS. At the same time, the add immediate instruction is limited to constants no larger than plus or minus 32,768. This keeps operations efficient within a defined memory window. Let's talk about J-type instructions, short for jump type. These are a specific format of instructions used in computing to handle jumps in the code. Essentially, they tell the program to move to a different part of the instruction sequence. The slide shows the general structure of a J-type instruction, which is designed to efficiently encode the target address for the jump. Understanding this format helps us see how programs control flow beyond simple, linear execution. Here, we see a couple of simple MIPS instructions. The first one loads a word from memory. Specifically, it grabs the value stored at an offset of 32 bytes from the address in register S3 and puts it into the temporary register T0. The second example uses the add immediate instruction, which adds a constant value directly to a register. In this case, it adds 20 to the value in S2, storing the result in S1. These instructions show how we handle data and constants efficiently in assembly. Let's talk about logical operations, the building blocks of decision-making in computing. These operations help us compare values, combine conditions, and control the flow of programs. Think of them as simple yes or no questions that guide what happens next. They're essential for everything from basic calculations to complex algorithms. Understanding how logical operations work gives us the power to create smarter, more responsive systems. Let's look at what happens when we shift bits in a register. Here, we start with a value in register S0, that's 25 in decimal. When we shift it left by 4 bits, it's like multiplying by 16. The bits move over and the new value becomes 400 in decimal, stored in T2. Shifting left pushes bits to higher places. The opposite operation, shifting right, moves bits down. These shift operations are fundamental for fast calculations and bit manipulation in computing. Let's break down some fundamental logical operations that work bit by bit. First, AND, it compares 2 bits and gives you a 1 only if both bits are 1. Next, OR, it's a bit more generous, giving a 1 if either bit is 1. Then there's NOT, it flips every bit, turning 1s into 0s and 0s into 1s. Finally, NOR combines OR and NOT, it outputs a 1 only when both bits are 0. These operations form the backbone of digital logic. Let's talk about the MIPS instruction set and its use of the NOR instruction instead of a direct NOT. NOR combines NOT and OR, so if one operand is 0, NOR acts just like NOT. For example, a NOR 0 is the same as NOT A. Here, we have some example values in registers T1, T2, and T3. When we AND T1 and T2, the result goes into T0. Same with OR. And when we NOR T1 and T3, T0 holds the bitwise negation of their OR. It's a clever way to simplify operations. In MIPS assembly, we make decisions using 2 key instructions, BEC and BNE. BEC stands for branch if equal. It tells the program to jump to a specific label if 2 registers hold the same value. On the other hand, BNE means branch if not equal. It directs the program to jump if the values differ. These conditional branches let us control the flow, much like an if statement with a goto in higher-level languages. They're the building blocks of decision-making in assembly. Let's look at how this simple C code translates into MIPS assembly. We're checking if variable A equals B. If they're not equal, we jump to the else branch. Otherwise, we add D and E, storing the result in C. After that, we skip the else part by jumping to the exit label. If A doesn't equal B, we subtract E from D instead. This example shows how conditional logic in C maps directly to jumps and arithmetic in MIPS. Let's look at how to translate this C code into MIPS assembly, keeping the instruction count as low as possible. We start by calculating the address of save I. Since each integer is 4 bytes, We multiply I by 4 using a shift-left logical instruction. This shifts the bits of I 2 places to the left, effectively multiplying by 4. We store this result in a temporary register, preparing to access the array element at that calculated offset. This step is key to handling byte addressing correctly in MIPS. Here, we're working with assembly instructions to access and compare elements in an array. First, we calculate the address of save at index I by adding the base address in S6 to the offset in T1. Then, we load the value at that address into a temporary register, T0. Next, we compare this value with S5. If they're not equal, we jump to exit. Otherwise, we increment our counter in S3 and jump back to loop to continue processing. An instruction set architecture, or ISA, is the blueprint that defines a whole family of microprocessors. Think of it as the contract between hardware and the low-level software that runs on it. It includes the actual instructions, the rules for using them, how they're written, and how the processor understands them. Keeping the ISA consistent lets manufacturers create many different versions of a processor. For top performance and energy savings, the ISA needs enough registers, and compilers must use them well. MIPS is one example of a RISC-based ISA. Let's talk about the MIPS instruction set architecture. It's built around simplicity, a small set of instructions and addressing modes designed to work smoothly with high-level programming languages. MIPS supports parallel execution, cutting down the work each instruction has to do. It also offers a large set of registers, which means less need to access slower main memory. All instructions are a fixed 32 bits wide, with uniform encoding. This keeps control logic simple and lets us use more registers. Instructions fall into categories like arithmetic, control, load store, and others. There are 3 main encoding formats: R-type, I-type, and J-type. Let's talk about how a computer stores data and instructions in memory. Memory is made up of millions of tiny storage cells, and each cell holds just one bit, either a 0 or a 1. A single bit is a tiny piece of information, so memory groups bits together into units called words. The size of these words is called the word length. Most often, a word is 8 bits long, which we call a byte. This organization helps the computer store and retrieve data efficiently. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about memory and how it's organized. Memory is like an array made up of m number of words, and each word is n bits long. Every word has its own unique address, which helps the processor find exactly where to read or write data. The number of address lines on the processor determines how many memory locations it can access. For instance, with 16 address lines, the processor can address up to 65,536 different memory locations. It's all about how many addresses the processor can handle. This table lays out the direct connection between memory capacity and the number of address lines. Essentially, each additional address line doubles the amount of memory you can access. So, as the address lines increase, the memory capacity grows exponentially. Understanding this relationship helps us grasp how systems scale their memory and manage data efficiently. It's a fundamental concept in computer architecture that underpins everything from small devices to massive servers. Let's talk about how memory is organized in terms of bytes and words. An 8-bit unit is called a byte. That's pretty standard. But when we move to larger word sizes, like 16 to 64 bits, we just call those words. Each byte within a word has its own unique address. So if the processor uses 32-bit words, each word is made up of 4 bytes, and those words are stored at addresses spaced by 4, like 0, 4, 8, and so on. This system is what we call byte addressability. Let's talk about how byte addresses get assigned across words. There are 2 main ways: big-endian and little-endian. In big-endian, the lower byte addresses hold the more significant bytes, the ones on the left side of the word. Little-endian flips this. The lower addresses store the less significant bytes, the ones on the right. This difference might seem small, but it's crucial for how computers interpret data in memory. The slide shows this clearly in the accompanying figure. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's take a closer look at how data is stored in a computer's memory, using a few examples. We'll interpret the same set of stored data in different ways to see how the format changes the meaning. First, we'll consider big-endian storage of 2 hex words, each 4 digits long. Then, we'll look at big-endian storage of 2 BCD words. Next, we switch to little-endian storage in ASCII for a signed 4-digit hex word. Finally, we'll examine little-endian storage in ASCII for a 4-digit BCD word. This helps us understand how data interpretation depends on both format and order. Let's break down how data is stored differently in big-endian and little-endian systems. In big-endian storage, the most significant byte goes into the lower address. For example, the hex words 3834 and 3239 translate to decimal values 14,388 and 12,857, respectively. When these are stored as BCD, the values remain the same as their decimal equivalents. On the other hand, little-endian storage reverses the byte order. For instance, the ASCII representation of the hex word 9248 converts to 37,448 in decimal after adjusting for the ASCII offset. Similarly, the BCD value 9248 directly corresponds to 9,248 decimal. This distinction is crucial when interpreting stored data correctly. Let's look at how to represent the number 81,234,561 in 2 common memory formats, 32-bit big-endian and little-endian. Big-endian stores the most significant byte first. That means the highest value part of the number comes first in memory. Little-endian does the opposite. It stores the least significant byte first, putting the smallest part of the number at the start. Understanding these formats is key when working with low-level data or different computer architectures. Let's talk about word length and alignment in memory. Typically, word lengths come in multiples of 8, like 8, 16, 32, or 64 bits. When word lengths go beyond 8 bits, we need to be careful about how we access them. For example, with 32-bit words, natural boundaries happen at addresses 0, 4, 8, and so on. Words starting at these boundaries are called aligned, which is what we usually aim for. If a word starts at any other address, it's unaligned, and that can cause issues. Let's talk about word alignment in a machine, especially one based on a microprocessor. Word alignment means arranging data so that words start at addresses that are multiples of their size. This makes memory access faster and more efficient. For example, with 16-bit words, aligned addresses might be 0, 2, 4, and so on. For 32-bit words, they jump in steps of 4, like 0, 4, 8. And for 64-bit words, the addresses increase by 8 each time, 0, 8, 16. This pattern keeps everything neatly aligned in memory. We've learned that numbers are stored in memory as words, so we access them by their word address. Characters, however, are stored as bytes, and we access them by byte address. When it comes to character strings, they're stored in consecutive memory locations. Because strings can vary in length, we need 2 things to work with them: the starting address and the length. The length can be indicated either by a special end-of-string character or by a separate length value stored elsewhere. This lets us access strings efficiently, either by their start address alone or with both address and length. Let's look at an example with a computer using byte-addressable memory, organized in 32-bit words with a big-endian scheme. Imagine a program that reads ASCII characters from a keyboard and stores them starting at memory location 1000. When the name Johnson is entered, each letter's ASCII code fills successive bytes. The first word at 1000 holds the codes for J, O, H, and N. The second word at 1004 stores S, O, N, and 1 unchanged byte. This shows how data maps neatly into memory words. We know that both program instructions and data live in memory. To run a program, the processor first fetches the instruction, then reads any data it needs, the operands, from memory. After it finishes the work, it might write results back to memory. So memory access boils down to 2 key operations: load and store. Loading means reading data from memory, while storing means writing data back. The processor tells memory what to do by sending an address and a read or write signal, making sure the right data moves in the right direction. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about the store operation. This is how the processor saves data into memory. The processor sends the address of the memory location where the data should go, along with the actual data itself. It also triggers a write signal to tell memory to store that data. Memory then finds the right spot and overwrites whatever was there before. This transfer usually happens between the processor's registers and memory, moving either a byte or a whole word in a single step. Registers are small but powerful. Each holds a word of data and acts as either the source or destination in these transfers. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. At the heart of every computer is a set of instructions, a toolkit that lets us tackle any data processing task. Whether a computer has 100 instructions or 300, these instructions need to cover a few essentials. First, moving data between memory and processor registers. Then, performing arithmetic and logic operations on that data. Next, managing the flow of the program itself, sequencing and control. And finally, handling input and output. These basics keep everything running smoothly. So far, we've looked at how data moves inside a computer system, between processor registers, memory, and the input-output system. To keep track of these transfers, we use a standard set of notations. Processor registers get labels like R0, R1, and R2. Memory locations are named something like LOC, place, or MEM. And for I/O registers, we use names such as DATAIN and DATAOUT. This system of nomming helps us clearly describe data movement. It's called register transfer notation. When we want to talk about the contents of a register or a memory location, we put square brackets around its name. This tells us exactly what data we're working with. For example, if we write R2 gets the contents of LOC, it means the data stored at LOC moves into register R2. Or, if we add the contents of R1 and R2 and store the result in R3, we write it like that. These expressions are called register transfer notations. They show how data moves and changes inside the processor. Assembly language notations are another way we represent machine instructions and programs. They use a specific format that's easier for humans to read than raw binary code. You'll see familiar names here. Register names and memory locations are the same as in register notations. For example, when we write move R2, R1, it means the contents of register R2 are copied into register R1. R2 stays the same, but R1 gets overwritten. Another example is ADD R1, R2, R3, which adds the values in R2 and R3, then stores the result in R1. Here, we're looking at a simple assembly language expression. It tells us to add the contents of registers R1 and R2, then store the result in R3. Notice the three parts: the operation, the sources, and the destination, arranged from left to right. This order is common, but not universal. Some computers flip the source and destination positions, so it's important to know the convention your system uses. Every instruction a CPU executes is made up of specific parts. We call these the elements of an instruction. First, there's the operation code, or opcode. This tells the CPU exactly what operation to perform, encoded in binary. Then, we have the source or destination operand fields. These point to the data the instruction will use or modify. Understanding these elements is key to grasping how instructions work at the most basic level. Next, we'll look at the main types of instructions the CPU handles. When the CPU runs an instruction, it often needs data to work with. These are called operands. The source operand is where this data comes from, either a CPU register or memory. Sometimes, the instruction points directly to the address of this source operand, so the CPU knows exactly where to find it. After the operation, the result usually has to go somewhere. That's the destination operand. The instruction tells the CPU where to store this result, specifying the destination address. Let's talk about the next instruction address. This tells the CPU where to find the next instruction once the current one finishes. For jump and branch instructions, the next address is built right into the instruction itself. But for most other instructions, the next one is simply the one that comes right after in memory. Now, instructions can vary in length, and they can reference different numbers of addresses, sometimes 3, 2, 1, or even none at all. This variety shapes how the CPU moves through a program. Let's talk about 3 address instructions. These instructions involve 3 variables, 2 sources, and 1 destination. For example, in the instruction ADD A, B, C, A and B are the source operands, and C is where the result gets stored. The general format looks like this: operation followed by source 1, source 2, and then the destination. To represent this instruction in memory, we need bits for each of the 3 addresses. That's 3 times the bits needed for one address, plus bits to specify the operation itself. Let's talk about 2 address instructions. These instructions combine 2 operands, one acts as the source, the other as both source and destination. For example, when we add it to B, the result replaces B's original value. This means B holds the sum after the operation. The format is simple: operation, source, destination. Because we only specify 2 addresses, fewer bits are needed to encode the instruction compared to 3 address instructions. Specifically, we need bits for both operand addresses, plus bits for the operation itself. Let's talk about 1 address instructions. These use a single explicit operand, while the other operand is always the accumulator, a special processor register. For example, ADD-B adds the value in variable B to the accumulator, replacing whatever was there before. The general format is operation followed by source. Instructions like load a copy data from memory into the accumulator, while store B moves data from the accumulator back to memory. The operand can be source or destination, depending on the instruction, but the accumulator is always involved. Let's talk about 0 address instructions. These are special because the locations of all operands are implied. You don't have to specify them directly. They're common in machines that use a pushdown stack to store operands. Now, when we compare instructions by how many addresses they include, fewer addresses mean fewer bits are needed to represent them. That also means fewer memory accesses, which makes execution faster. So, instructions with 3 addresses take longer to execute than those with just 1, simply because they require more memory access. To speed up execution, we need to minimize memory accesses in our instructions. Instead of fetching operands directly from memory, it's better to use processor registers. These registers are much faster to access. When compilers translate high-level code into machine language, they work smartly to keep most operand references in these registers. This reduces delays and makes programs run more efficiently. It's a simple shift that has a big impact on performance. Let's look at how we can evaluate the expression y equals the sum of A and B, multiplied by the sum of C and D, using different instruction formats. First, with 3 address instructions, we add A and B into one register, C and D into another, then multiply those results. Next, with 2 address instructions, we move values into registers, perform additions updating those registers, multiply, and finally store the result in Y. This example shows how the same calculation adapts to different instruction styles. Here, we're looking at 2 different ways to perform the same calculation using assembly instructions. First, with 1 address instructions, we load values, add them, store intermediate results, and finally multiply and store the outcome. It's a step-by-step process with explicit memory references. Then, with 0 address instructions, everything happens on a stack. We push values, perform operations directly on the top of the stack, and pop the final result into memory. It's a more compact, stack-based approach that simplifies addressing. Let's look at how to evaluate the expression x equals a times the quantity b plus c times the sum of d and e, all divided by f times the sum of g and h. Will start with 0 address instructions, which use a stack to manage operations. We push d and e, add them, then multiply by C next. We add B, multiply by A, and then handle the denominator by pushing G and H, adding them, multiplying by F, and finally dividing. The result is popped into X. This approach shows how stack operations simplify complex expressions. Here, we have a program written using one-address instructions. Each line shows an operation and the memory location it works with. For example, we start by loading the value at H into the accumulator. Then we add the value at G, multiply by F, and store the result at T next. We load D, add E and B, multiply by A, and finally divide by the value stored at T. The final result gets stored at X. This sequence illustrates how complex calculations can be broken down step by step with simple instructions. Let's look at how the expression X equals A times B plus C times C is executed in different processor types using an accumulator organization. For a one-address processor, we start by loading A into the accumulator, multiply it by B, and store the result temporarily. Then, we load C, multiply it by itself, add the previous result, and finally store the sum in X. This step-by-step approach shows how the accumulator handles operations sequentially with minimal addressing. Here, we're comparing two ways to handle instructions in assembly language. First, with two-address instructions, each step moves data between registers and memory, often requiring multiple moves and operations to get the job done. It's a bit more step-by-step. On the other hand, three-address instructions let us do more in a single line, multiplying two values and storing the result directly in a register, for example. This approach can make the code shorter and more efficient, reducing the number of instructions we need. We've learned that instructions in a processor can be just an opcode, or an opcode combined with operands or addresses. Every processor supports basic instruction types, like data transfer, arithmetic, logic, and branching. To get a task done, the programmer must carefully choose and arrange these instructions in the right order. This process is called instruction sequencing. When these instructions are lined up to perform a specific job, we call that a program. This slide introduces how instructions execute in a straight-line sequence. When a processor runs a program, it relies on something called the program counter, or PC. The PC holds the address of the next instruction to execute. At the start, the PC is loaded with the address of the program's first instruction. From there, the processor fetches and executes instructions one by one, moving through memory in order. This process is called straight-line sequencing. After each instruction runs, the PC advances by the instruction's length, so it always points to what comes next. Sometimes, we can't store a program in consecutive memory locations. After a decision-making instruction runs, the program has to choose between two different paths. This means straight-line sequencing won't work anymore. Instead, we use branch instructions. These let us jump from one sequence of instructions to another. Branching is how programs handle choices and changes in flow, guiding the control where it needs to go next. This slide sets the stage for understanding that process. Let's look at a simple program that calculates the absolute difference between two numbers. A and B. The key is to check which number is larger. If A is greater than B, we subtract B from A. Otherwise, we subtract A from B. The program moves the values into registers, compares them, and then jumps to the right sequence based on that comparison. Finally, it stores the result in a register for later use. This ensures the operation always gives a positive difference. In this part of the program, we use the JB next instruction to jump to a different point if one value is less than another. This kind of jump is called a conditional branch. It only happens when a specific condition is true. When we branch, the program counter loads a new address, called the branch target, and starts executing from there instead of moving on sequentially. These conditional branches are key for loops, letting us repeat instructions multiple times, like adding 10 numbers stored one after another in memory. Let's talk about the program loop, the core structure that makes a processor repeat a sequence of instructions. It has 4 key parts. First, the initialization section sets up starting values, like loop counters and memory pointers. Next, the processing section is where the actual work happens. The data gets manipulated here. Then, the loop control section updates those counters and pointers for the next round. Finally, the results section analyzes and stores what the loop has produced. Together, these parts keep the loop running smoothly. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's break down how a typical program loop runs. The processor handles the initialization and results sections just once, but the processing and loop control sections, those can run many times. So the total time spent in the loop really depends on how long those two sections take. In the first flowchart, the processing section always runs at least once. But if you swap the processing and loop control sections, it's possible the processing might not run at all, if the conditions say so. This subtle change can affect how your program behaves. When a program runs, certain operations produce results that need to be tracked. That's where condition code flags come in. These flags live in the status register, sometimes called the flag register. After arithmetic or register operations, specific bits in this register get set or cleared. These bits aren't just passive, they enable the processor to make decisions. By checking these flags, the program can change its flow, taking different paths depending on the conditions it encounters. This is how logical decisions happen at the hardware level. Let's break down some key status bits that tell us a lot about what's happening inside a processor. First, the carry or borrow bit. It's set when adding two 8-bit numbers goes beyond the maximum value, or when subtracting a larger number from a smaller one. Next, the 0 bit, it flags when a register ends up with 0 after any operation. Then, the negative or sign bit, it's the most significant bit in 2's complement, showing if a result is negative. Finally, the auxiliary carry bit, it tracks carry between the lower and upper halves of a byte, especially useful in decimal calculations. These bits help the processor keep track of its math, step by step. Let's talk about the overflow flag in 2's complement arithmetic. Here, the most significant bit represents the sign, while the rest show the number's magnitude. The overflow flag triggers when a signed operation's result is too large to fit in the available bits. For example, adding two positive numbers might produce a binary result that looks correct, but it actually exceeds the allowed range, setting the overflow flag. Then there's the parity bit, which is set when the result has an even number of ones. Sometimes, we specify a memory address directly in an instruction, like MOV 2000H, R1. Here, the address is fixed. It doesn't change as the program runs. But often, we need to access different memory locations dynamically. For example, when adding up all elements in an array, we repeat the addition for each item, moving to the next memory address each time. This slide introduces how we generate those changing memory addresses in a program. Let's talk about indirect addressing, a way to change the memory address each time we enter a loop. Instead of using a fixed address, we use a register that holds the address, like R2 in this example. By incrementing R2, we move through different memory locations step by step. The instruction ADD R1, R2 adds the value at the address in R2 to R1. This technique lets us process arrays efficiently, updating the pointer and counter as we go. When we talk about programming flexibility in processors, a big part of it comes down to how the processor refers to data in memory or input-output devices. These methods are called addressing modes. The processor calculates what's called an effective address. That's the actual location it uses when accessing data or instructions. This effective address can be built from up to 3 parts: a base, an index, and a displacement. Addressing modes define exactly how these parts come together to find the right data. When we talk about addressing modes, we're really looking at the different ways a processor can access data. There are quite a few 12 key types to keep in mind. They range from register addressing, where data is right in the processor's registers, to more complex modes like indirect or displacement addressing, which involve memory locations calculated on the fly. Some modes even adjust pointers automatically, like auto-increment or auto-decrement. Each mode offers a unique way to handle data, making the processor more flexible and efficient. Let's look at a simple example, MOV R2, R1. This instruction copies whatever is in register R2 into register R1. It's a straightforward way to move data inside the processor. This is called register addressing mode, where the operand, or the data we're working with, comes directly from a register. The instruction itself tells the processor which register to use by name. It's fast, efficient, and fundamental to how processors handle data. Let's look at 3 ways instructions can specify where to find their data. First, absolute or direct addressing. Here, the instruction directly includes the exact memory location. For example, moving data from address 2000 into a register. Next, immediate addressing. The instruction itself holds the actual value to use, marked by a special symbol like a hash. Finally, indirect addressing. The instruction points to a memory location that, in turn, points to the real data. Each method offers a different way to access information. Now, let's explore 2 important addressing modes. First, register indirect addressing. Here, the effective address comes from the contents of a register or a memory location specified in the instruction. For example, MOV R0. Copies data from the memory location pointed to by register R0 into register A next, displacement addressing. This mode adds a value to the contents of a referenced register to find the effective address. It blends direct and register indirect addressing, with common types like relative, base register, and index addressing. Let's talk about relative addressing mode, also called PC relative addressing. Here, the program counter, or PC, is the key player. The effective address is found by adding the PC's current value to the address part of the instruction. That address part is signed, meaning it can point to a location before or after the current instruction. This makes it perfect for branch instructions, like jumping to a label if a condition is met. For example, JNZ back sends the program to back if the condition holds true. Let's talk about 2 important addressing modes in computer architecture: base register addressing and index addressing. In base register addressing, the register holds a main memory address, and we add a displacement, a small number, to find the exact location. For example, MOV R+8, copies data from the address at R+8 into register A. Index addressing works a bit differently. Here, the address field points to a memory location, and the register provides an offset from that address. This lets us efficiently access data stored sequentially, which is great for looping through arrays or lists. Both methods help us navigate memory in flexible, powerful ways. Let's look at 2 addressing modes with examples. First, the basic one here, the memory address comes from a register, plus a displacement from another register. The value at that combined address gets copied into a register. Simple enough. Next, auto-increment addressing. This one uses a register's contents as the address, but after accessing it, the register automatically increments. So, if you copy data into the address held in register 2, that register moves to the next location right after. It's a neat way to step through memory efficiently. Let's look at 2 important addressing modes that help us manage memory efficiently. First, auto-decrement addressing. Here, we decrease the value in a register before using it to access memory. For example, when we say MOV-R0 to R1, we first subtract 1 from R0, then use that new value to find the memory location, and finally copy the data into R1. Next, stack addressing mode involves a stack pointer that always points to the top of the stack. This pointer tells us exactly where to find or place our data in memory. Now let's look at a special kind of addressing mode, one that uses the stack pointer as the referenced register. The stack usually grows downward, from higher to lower memory addresses. When we push data onto the stack pointer moves down first, then the data is stored. When we pop data off, the pointer moves back up. For example, the instruction push R decreases the stack pointer, then copies the contents of register R onto the top of the stack. It's a neat, efficient way to manage data. Let's talk about MIPS addressing modes, starting with immediate addressing. Here, the operand, the data we want, is actually part of the instruction itself. It's a constant value baked right in. For example, the instruction LUI S0, 61 loads the number 61 directly into the upper 16 bits of the register S0. This mode is straightforward and efficient when you know the exact value you need at compile time. Next, we have register addressing. This mode uses registers directly as operands. For example, when we say add T1, S0, S1, we're adding the values stored in registers S0 and S1. Then, the result goes straight into T1. It's a fast, efficient way to work with data already inside the processor, avoiding slower memory access. This makes register addressing a key tool for quick calculations. Next, let's look at base or displacement addressing. Here, the operand's location in memory is found by adding a constant value, called an offset, to the address stored in a register. For example, if we have an instruction like load word, with T2 as the base register and 4 as the offset, the effective address is T2 plus 4. The data at that combined address is then loaded into T1. It's a simple but powerful way to access memory relative to a base location. Let's talk about PC relative addressing. This mode calculates the branch address by adding a constant value from the instruction to the current program counter, or PC. It's a way to jump to a location relative to where we are now in the code. For example, the instruction, bec $0, $3 label, means branch if equal, using that relative address to find label. It's a simple but powerful way to control flow efficiently. Next, we have pseudo-direct addressing. This mode uses 26 bits from the instruction itself, combined with the upper bits of the program counter to form the jump address. One key detail, the address must be a multiple of 4. This ensures alignment in memory. For example, a jump instruction like JLabel tells the processor to go directly to the location labeled in the code, using this combined address format. It's a compact way to handle jumps within a certain range. So far, we've looked at different instructions that a processor can handle, all written in assembly language. But before the processor can run these instructions, they need to be translated into machine language, the only language the processor truly understands. Each instruction has an operation code, or opcode, plus one or more operands. These operands might be numbers, addresses, or registers. To capture all this, every instruction gets a unique machine code, a compact, encoded bit pattern that includes the operation, operands, and the addressing mode. This process is called instruction encoding. So far, we've looked at instructions that do things like add, subtract, move, shift, rotate, and branch. These instructions work with different operand sizes, 32-bit numbers, 8-bit numbers, or even 8-bit ASCII characters. The operation type and operand types are identified by a binary code called the opcode. If we use 8 bits for the opcode, that gives us 256 possible instructions. The remaining 24 bits hold other details, like which registers are involved. For example, an ADD instruction nomming 2 registers needs bits to identify each one, especially if there are 16 registers total. When we use the register addressing mode for each operand, we need extra bits to show that clearly. Take the instruction move 24, R0, R5. It requires 16 bits for the operation code and registers, plus bits to mark that the source uses index addressing with an offset of 24. For instructions like L-shift-R2, R0, or move 3A, R1, immediate values must be included alongside the 18 bits for the opcode and addressing modes. This limits immediate values to 14 bits. Finally, branch instructions like branch greater than 0 loop use 8 bits for the opcode and 24 bits for the branch offset. In these examples, every instruction fits neatly into a 32-bit word. We've got an 8-bit field just for the operation code. That's the command itself. Then, 2 7-bit fields specify where the data comes from and where it's going. Each 7-bit field tells us both the addressing mode and which register is involved, if any. Finally, there's a field for other info, things like an index or an immediate value that the instruction might need to work properly. It's a compact, efficient way to pack all the details in. Let's take a look at different instruction formats in computing. We've got one-word instructions, which are simple and direct. Then, two-word instructions add a bit more detail, often specifying an operation and a target. Finally, 3-operand instructions are more complex, involving multiple pieces of information to perform a task. Understanding these formats helps us see how computers process commands at different levels of complexity. It's all about balancing simplicity with the need for precision. When we talk about writing programs, there are 3 main language levels to consider. First, machine-level language. This is the raw binary code that the computer actually understands. It's made up of sequences of zeros and ones, directly telling the hardware what to do. But writing in machine language is tough. Programmers have to memorize thousands of these binary instructions, which makes it error-prone and complex. Then there's assembly language and high-level languages, which help bridge that gap. We'll explore how these levels interact next. When we write programs in assembly language, we're making things easier for ourselves compared to raw machine code. Assembly uses short words called mnemonics, usually 2 to 4 letters, that stand for specific instructions. For example, ADD means add, AND means a logical AND operation, and MOV means move data from one place to another. These mnemonics help us remember what each instruction does. Assembly language also has its own rules for syntax, like how lines are structured with labels, mnemonics, operands, and comments. This structure keeps everything clear and organized. Let's break down the structure of an assembly language instruction. First, there's an optional label field. This gives a symbolic name to the address of the instruction. It's like a bookmark we can jump to in the code. Next comes the mnemonic, which is mandatory. Every instruction needs one. It tells the processor what operation to perform. After that, we have operands, which vary depending on the instruction. Some have none, some 1, some 2, separated by a comma. Finally, there's the comment field, starting with a semicolon, used to explain what the instruction does for us humans. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Another way we write programs for microcomputers is by using high-level languages like BASIC, Pascal, C, or C++. These languages use statements that look much more like English compared to assembly language. Each statement here can translate into one or many machine code instructions. To make this happen, we rely on tools called interpreters or compilers. They convert our high-level code into the machine language the computer actually understands. This approach makes programming more accessible and efficient. When we write programs in high-level languages, we can do it much faster than using assembly or machine code. That's because one line of high-level code translates into many machine instructions. But there's a trade-off. These programs need to be interpreted or compiled before they run. That means they usually execute slower and use more memory compared to assembly language programs. This slide shows a comparison between machine code, assembly, and high-level languages, highlighting these differences clearly. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Computers only understand machine language, a string of zeros and ones. So we need translators to convert the human-friendly code we write into this machine language. These translators come in 2 forms, compilers and interpreters. A compiler takes the entire program, translates it all at once, and creates a file the computer can run directly. An interpreter, on the other hand, translates and executes one statement at a time, stopping immediately if it finds an error. Both play a crucial role in bridging the gap between us and the machine. To wrap up, let's quickly compare interpreters and compilers. Interpreters translate code line by line, making them great for testing and debugging. Compilers, on the other hand, translate the entire program at once, which usually means faster execution. Both have their strengths, and understanding these helps us choose the right tool for the job.